With the final part of this demo, we're illustrating how the controller can have a practical application by considering robotic tool use. Current control methods, either compliant or non-compliant, have to know in advance all the properties of a tool that might be used during operation. This limits robots to using tools designed specifically for them or which have been extensively modeled. However, when working in a natural environment, the characteristics of a tool are often unknown. A coworker might provide new tools to use, and a hammer can have many weights and shapes. Current methods will often fail with tools that aren't completely known beforehand. Some aspects of the problem of dealing with an unknown tool, such as identifying its shape, can be solved using a simple vision system. Here, the vision system has located the offset of the tool tip from the hand, which depends on whatever grip the hand happens to have. In the case of a wrench, the mass of the tool is low enough that the controller can ignore it and work reasonably well. Because we've switched the tool, the vision system is being used to calibrate the movements to account for the tool's changed shape. It makes two measurements to get a more precise estimate. However, the mass of a tool cannot in general be ignored, since the whole dynamic model of the arm needs to be updated when the mass changes. As seen here, the compliant arm does not perform well when given a hammer, because the mass is too large to be ignored and still perform reasonably. We'll now switch back to the adaptive controller. With the adaptive controller running, when we give it a heavy tool, on the first reach it has some error, but you can see that it immediately begins to adapt. So it is learning to account for both the shape and the mass of the tool. A tool it has no knowledge of beforehand. As in the case with the weight in the hand, you can see improvement after each reach to different targets. As before, we're now loading weights that we've trained on reaches for about half an hour with a hammer. Even though the placement of the hammer might vary, accounting for the mass is most important. Again, you can see on the first reach that it is quite good at handling the heavy tool. This concludes our demonstration of an adaptive, compliant neuromorphic controller. Over the last several months, the ABR team has created the visual system and all the controllers from scratch. To the best of our knowledge, this set of behaviors has not been demonstrated previously in a neuromorphic system. In particular, the continuously adapting motor controller is a unique technology that stands to significantly improve human-friendly neuromorphic robotics. Interestingly, it is exactly this kind of algorithm that DARPA's recently announced Lifelong Learning Machine initiative has highlighted as critical to the future of AI.